So welcome to the today's class. Today we are going to see lecture number 7, right? Okay. MOSFET behavior. Okay. MOSFET behavior. Okay. In the last class, we have already seen what are the mathematical equations that governs the operation of the MOSFET, right? And MOSFET that we have seen, right? So can you recap once? Can you recap once? So as we have seen in the last class, when the gate to source voltage is less than threshold voltage of a transistor, we said the MOSFET is off. Okay, which means that there is no current will flow from drain to source, which is equal to 0. Okay, so this is also called as a cutoff region. This is also called as cutoff region, right? Okay. So what is the second thing that we have seen? If VGS value is greater than or equal to threshold voltage of a transistor, then what we can say, the transistor is said to be on, inversion channel is formed, and whatever the ID that we can see from drain to source, which is not equal to 0. Okay, a finite amount of the current will flow, but what mathematical equation that governs this ideas? Okay, so if, for example, if VDS value is if VDS value is less than VGS minus of VTH, okay, under this condition, MOSFET actually said to be in linear region, which means that the current will follow the VDS value. How much VDS that you apply, the IDS also linearly increases. Okay, under this condition, what IDS that we have seen? Then in this condition, the MOSFET is said to be in linear. Okay, what is this IDS now becomes? Mu n Cox W by L into VCS minus of VT into VDS minus of VDS squared divided by 2, right? Right. So again, this is the one condition that we have seen, but another condition, there is another possibility that VDS value is greater than or equal to, or I can say this is greater than, okay, greater than VCS minus of VTH, then the MOSFET is said to be in saturation. The MOSFET is said to be in saturation. So under this condition, what is the current value? IDS is equal to half mu n Cox W by L into VCS minus of VTH whole square. So here the MOSFET is not following the VDS changes. Okay, how much you change the VDS value, you cannot see that much change in your IDS value. Okay, therefore it is remains constant. Okay, and we also said that this is how the graphically we have shown the behavior of the NMOS transistor. Okay, we applied the VDS and we have seen VCS. Sorry, we have seen IDS. This is also called as output characteristics of the MOSFET. Since we are talking about the output quantities. Okay, if we talk about this is a MOSFET, for example, this is an NMOS part, for example, this is the gate, this is the drain, this is the source, for example, and the current will flow from drain to source, that is called IDS. Okay. Therefore, we talk about the difference between the VDS to this IDS. Okay. This is usually we can call it as an output side kind of thing. If you consider this is a two-port network, for example, so this particular port is called output, and this particular port is called input actually. Okay. Okay. So now this characteristics is something like this. There is a linear relationship, and after that it is go and will be constant. This kind of behavior is can be seen provided the VGS value should be greater than that of the threshold voltage. Okay. So if suppose if it is less than the threshold voltage, we simply say that the IDS value is equal to 0. Okay. So therefore, this is what this characteristics is when VGS is less than VTH. So this characteristics is actually when VGS value is greater than VTH. So this is what we have learned in the previously by using some kind of the qualitative analysis. Okay. Now let us go and see the same mathematical equations for PMOS transistor. Okay, for PMOS transistor. Okay, let us see what is the PMOS transistor and under which conditions that will be on and off. Okay. So first of all, I am going to give you the current values and all. Okay. And one by the by, just you can understand here whatever the quantities that we talk about. Therefore, for example, VZ, okay, VD, VS, and you know the VTH, all are and IDS, all are positive quantities. All are positive quantities. Okay. Now, whereas for the PMOS transistor, it should be all are negative quantities. We talk about this one why it is negative by taking some example, right? Okay. So for the time being, just I want to give you the let us give some kind of explanation on this particular one, and we'll come back and we will analyze step by step. Okay. So here, the PMOS is actually complement to the NMOS transistor. Okay. On what basis you can say it's a complement? For example, if you take the source and drain, instead of the N plus, we take the P plus. Instead of the channel is N channel, we take the P channel. Instead of applying the positive potentials, we apply the negative potential. Instead of taking the P as a body for the NMOS, N for the body for the PMOS. That's the reason why it's almost to complement each other. That's the reason why all are negative quantities, and whatever the current that you see, it's a negative quantity. Okay. And one more thing is that you look at this one. Okay. So this is actually instead of the, okay, let me consider it. Yeah. So instead of a positive, this is what we can say. If the VGS is greater than VTH, then the transistor is said to be off. Okay. We'll explain this one a little bit later. Okay. Now, for example, if this is the case, for example, if this value is less than or equal to VTH, for example, then the transistor is said to be on transistor. And just you have to consider this is also instead of the negative, I'm so sorry. Yeah. So it should be greater than. When VDS value is greater than VGS minus a VTH, it's said to be in linear. And instead of writing this is a P, we need to write mobility of the holes that we have to write. Okay. And instead of this greater than, we have to write for less than for the saturation. Okay. Instead of the NMOS N, we have to write E here. Okay. Just this is what these are the one. Okay. And one more thing is that it's a negative current. Okay. We have to take minus. IDS is a minus. This is also minus. Okay. We'll come to this one by explaining some concepts. Okay. So therefore, if VCS is greater than VTH, then it is off. VGS is less than VTH, this is on. If it is on, we should say whether it is a linear or saturation. When it is a linear, when VGS value is greater than VGS minus the VTH, this is in linear. If it is less than VGS minus VTH, saturation. Okay, just it is opposite, that's it. And the current, whatever the current we see, that is a negative. Okay, now let us go and understand very important thing. Okay, so we take a MOSFET again. Okay, so what is the structure of the MOSFET here? You look at here. Okay, similarly, we take a PMOS transistor as well. Okay, we take an NMOS transistor and PMOS transistor. What is the substrate here for the NMOS? P substrate. What is the substrate for NMOS and PMOS transistor? N substrate. Okay, we know very well that we have a oxide on top of it. Okay, and there is a polysilicon on top of it. Here also we have a oxide. On top of it we have okay. Now what are the source and drains? Source is actually N plus. Let me call this is the drain. This is also N plus. And here the source is, for example, P plus, and the drain can be called as N plus. Right? Okay. Now, if you want to form a channel, okay, as we have also seen that there is a one potential here, therefore one terminal here, therefore there is another terminal here, and there is another terminal here. Okay. Here also one terminal here. Okay, sorry. 1, 2. So assume that the body is actually same as the source. Okay. Whatever the potential is there for the source, the same potential is for the drain also. Assuming in that way. That's the reason why I'm not showing the drain potential. Okay. So it is an NMOS transistor, right? Okay. What potential that I should apply for the gate? Let me consider this is the gate potential here. The drain potential here is the source potential. Here also gate potential, source potential, and drain potential, assuming in this way. Okay. Now tell me what potential I have to apply at the gate of the NMOS transistor? Positive or negative? Positive. All right. Whenever if you apply a positive potential, then only the channel will be formed. If you apply negative potential, the channel cannot be formed. It never form a channel, right? Okay. Therefore, what I'm going to do here is that it is a negative potential. Sorry, positive potential. What about the gate source? It should be negative. Okay, it should be negative. So, since if you apply the positive potential at the VC, then channel will be formed. Therefore, VC potential is responsible to get that one. And the source is at negative potential, can push the electron from the source to drain side. That's the reason why it should be negative. Okay, this is what the potential that I should apply. Agreed? Okay, right. So similarly, what is the potential I have to apply between the drain and source? Okay, for example, we consider only these two things only. Okay, we'll come back to that one. Similarly, what about here for PMOS? If you want to form a PMOS, the channel, what kind of potential I should apply? Negative I have to apply at the gate. Gate should be negative. What should be potential of the source? positive, right? Am I doing that? Did you catch this point? Okay. Now, why VCS should be greater than the threshold voltage? Why VCS is less than threshold voltage for the PMOS transistor? Okay. Okay. So what this is called, let me call this is VGS now. Okay. Now this is called, let me call this is also VGS, for example. This is also VGS, for example. Okay. Right. Look at the point here. So assume the threshold voltage of a PMOS transistor is N is equal 1 volt plus 1 volt. Okay. Assume the threshold voltage of a PMOS transistor is minus 1 volt. Minus 1 volt. You can on the screen. Do you feel any difficulties looking at the screen, or if you want to go the side? Is that okay? Okay. If you're not comfortable, just go and sit there. No, not a problem. Okay. Yeah. So and the VTS is equal to 1 volt and the VTHP is minus 1 volt. Okay. What is happening here? Okay. Let us take a simple scale here. Okay. This is very important. Don't confuse later. Okay. So let us consider this is a 0. This is 0. And this is, for example, 0.5. 0.5 volts. This is 1. This is 2. This is 3. This is 4. Let us come here. Minus 0.5. Minus 1. Minus 2. Minus 3. Okay. Let me take the same thing here. Copy. And I want to paste here. Okay. Now tell me, what is the condition that the transistor is said to be on for the PMOS transistor? Sorry, NMOS transistor. What is the condition? VCS value should be greater than threshold voltage. If this has happened, then the transistor is said to be on. When the VCS value is greater than threshold voltage of a NMOS transistor, the transistor is said to be on. That means the difference between the gate potential and the source potential should be a positive quantity. Is that point is clear? And that means if I say this is actually the voltage that is for the this much voltage that we have to apply. Undoubtedly, we have to apply plus 1 volt to the PMOS transistor. The difference between the gate and source must be plus 1. More than plus 1, actually, we can say. Then only the transistor will be on. That means you can say for all these voltages, what will happen? For all these voltages, MOSFET is said to be on. The voltage is below this one. That means less than 1 volt. For all these cases, what we can say about the MOSFET? MOSFET is said to be off. That means when the VCS value, that means when the VCS value is less than, sorry, greater than the threshold voltage of a transistor, for all these values from plus 0.5, 0, minus 0.5, all this, whatever the values that are there in the negative side, it will be 0. If I say that the threshold voltage of a transistor is at 3 volts, for example, so it won't be like that, 3 volts, then when it will be on, VGS should be more than 3 volts. Below 3 volts, whatever the voltage that you apply, the VGS values, whatever the value that you apply, will the transistor will be on? No, it won't. Right? So that means when the gate potential is positive, okay, what we observe this one, when the gate potential is positive, if you apply, what we can see, that potential should be more than that of the 1 volt. That means what is the result of this plus value? It should be more than that of the plus 1 volt. Then only the electrons will be induced at this place. Am I right? If you apply more positive, for example, if you apply more positive, then what will happen? More positive, that means that what we are seeing that means we are going towards this this side. Okay, we are going towards this side. Okay, then what will happen? More carriers will be induced, right? More free carriers are available. You get the point? So therefore, when the more carriers are available within the silicon dioxide, under the silicon dioxide, definitely the channel will be available. Therefore, we said the MOSFET is set to be on. Channel is present, then you should say that the MOSFET is on. Okay, that means for every positive value of the VGS, more than that of the threshold voltage, the channel is available. Therefore, MOSFET is set to be on. If you apply the negative potential, if the potential of VG is less, for example, VGS is negative values, will this be channel will be formed? No, channel cannot be formed there, right? Okay. Now the question comes here is that okay, this is a simplest thing to understand, okay? But the question comes here is that whenever we're talking about the electronic circuits, for example, okay, for example, look at this particular one. This is the MOSFET. This is the NMOS transistor. This is the gate potential. This is the drain potential, drain terminal. This is the source terminal, for example. Okay. Now, the question is that means this is actually this particular terminal is connected from so and so network. Okay. This is also connected with so and so network. Okay. It is come and connected to this one. This is also come and connected to this one. Okay. Then what is the potential of this one and what is the potential of this one? Make this transistor is on or off. That's what important actually. For example, I want to say that this transistor should be on. Then what is the conditions of VC and VS? What is our requirement? Our requirement is that VCS value must be greater than threshold voltage. That means what is the VC actually? VC minus of VS. This value is actually the difference between these two must be positive. It must be a positive, that too more than 1 volt. It's more than 1 volt. It should be a positive quantity, undoubtedly, but that is also more than 1 volt. Because positive means that 0 is a positive quantity, minus 0.1 is also positive quantity, 0.2 also positive quantity, 0.5 is also positive quantity, but not for all the values of the positive quantity. What is the value? Plus 1 volt. Okay. Now, what is the chance that what is the values of the VC? What is the values of the S makes this is a positive? Okay, forget about 1 volt, but positive value. If you are increasing the VC in the positive direction, keeping the VS is constant. If you are increasing the VC, potential of the gate is positive direction, and keeping the source is at a constant potential, then definitely VCS value is positive. Or keeping the VC is constant, and the source is at a more negative. Source is at a more negative, then VCS can be positive. Okay, that means if you want to make this transistor, always remember that one. This should be always. What is the requirement? Okay, if you the requirement for the, let me write here. Okay, or more clearly, let me write it in this way. Look at this carefully. For example, this is a 5 volts, 4 volts, 3, 2, 1, minus okay, 0.5, 0, minus 0.5, minus 1, minus 2, something like this. It is the VG side. The VS side is something like this. This is also 5, 4, 3, 2, 1, 0.5, 0, minus 0.5, okay, minus 0.1, so not 0.1. Let me call it as 1, minus 1, minus 2, minus 3, minus 4, something like this. Look at it carefully. What VC, which direction VC has to be by keeping the sources, for example, 0. For example, keeping the sources at VC, sources at 0. Okay. And what direction I have to go, upwards or downwards, to make the VCS is positive? It must be opposite direction. As you can see that, suppose 0, okay, for example, 0 minus, okay, where it will start? What is the minimum value I can start with VC? Can I start with 0 onwards? No. Okay, 0 minus of 0 cannot be possible. That's 0.5 minus of 0 cannot be possible. 1 minus of 0 can be possible. Why? Because threshold voltage is it's equal to V3 threshold voltage. The channel can be formed. Okay. If you go for the 2 minus of 0, 2 minus of 0 more than the threshold voltage. 3 minus of 0. Like this, I can go. If I go here from this, okay, like this I can go. So that means VC can go up, right? Okay. So therefore, the required situation, I can say, the required situation on VGS. The required situation on VGS to make transistor is on, to make NMOS is on. What is the condition? What is the condition? The condition is VC must be increasing direction. VC must be increased. Okay, this side must be increased. That means whatever the potential that is coming from other circuitry to this particular transistor, it must always in the positive direction. Okay. What about the VS now? What is the VS? What you can expect? Therefore, whatever the value that you can take, if you take, for example, this one, for example, this one, for example, 2 minus of, for example, okay, for example, 1 minus of minus 0.5, 1 minus of minus 0.5. What is the difference here now? VC minus of VS. What is the value? VC is 1 volt minus of, what is the VS? Minus 0.5. What is the value? 1 volt, 1.5 volts. Minus plus, it becomes 1.5 volts. It's more than the threshold voltage, right? If you go and this one, keeping the VG is constant, and go and decrease the values of the source. Okay, what you can expect? Definitely, the VGS becomes positive. Okay, that means what is the required condition for VS? It should be more negative. It should be more negative. As long as VS is more negative, as long as VC is more positive, then definitely the transistor becomes on. Is that point is clear? Okay, so that is what the requirement of the VGS to become the transistor is on. Okay, okay. Now let us go and understand about the PMOS transistor. Okay, what you don't want actually, suppose if you want to, what is I can say that different way. What is the required situation on VGS to make NMOS transistors off? What is the chance? See, one thing is very important. Fix this one condition you can see. Let us consider VG and VS here. Okay. So if the VGS is increases, okay, what are the different possibilities? For example, either VG can increase, VS also can increase. Okay, either VG is increase, I can say that the lower to higher I'll go. Okay, but I'll go from lower to higher. Something like this. Look at this one. Both can decrease. One possibility. This can decrease and this can increase. This can increase and this can also increase. This can increase, this can also increase. Therefore, which condition makes the transistor on and off? What about this condition? since this particular VC is actually the lower, that means I can say that low means that negatives, for example. I can simply say that negatives. For the negative values of the VC, undoubtedly, it's off. Undoubtedly, it's off. Negative values of this one, provided VS must be constant. Okay. So therefore, generally this will be, okay, this is also negative. Let me give one example on this one. In this particular case, VC is a negative. It will be going down actually. VCS is gate potential is going down, for example. Okay. What about the source potential? Source potential also decreasing, for example. Drain for gate potential is decreasing. Source potential is also decreasing. What does that mean? The transistor is said to be off condition. Okay. It can be off condition. Okay. Assume that in this case, decreasing in the sense negative. Okay. This is also decreasing in the sense negative. Okay. So this is actually, in this case, is definitely, this case is definitely off. Actually, this upper case may not be definitely true. Okay. But this case is definitely off because it is a positive direction. Okay. In the positive direction. Which condition that you can see that is the one in this particular one? So since the gate potential is less, okay, let me write it as one example. VC minus of VS, right? Okay. In this case, VC is negative. That means, for example, minus 1 volt, for example. Okay. And source potential is positive side. For example, plus 1 volt, for example. Then definitely what will happen? Minus 1, that becomes minus 2. Okay. For example, this is, for example, minus 2, for example, the VC. Then the positive direction, VS, for example, plus 3, for example, let me consider. So what is happening? Minus 5. Undoubtedly, this condition becomes off. That means we never try to go and increase the drain potential and the decrease the VC potential, the negative direction, and should not increase the source potential in the opposite, in the positive direction. Okay. So therefore, it should not be happening. Okay. These words, whenever we are realizing the circuits, I'll ask this kind of questions in between. So you should be in a position to explain this. Okay. Right. Now, what about this one? Okay. What is the damp sheet condition that the transistor is on? First, the damp sheet conditions we'll talk about. And what is that? Increasing VS is, okay, I did wrong actually. Increasing and decreasing. This is a wrong thing. Decreasing. This is increasing and increasing. Okay. Now this is what actually damn sure that you will get on transistor. Okay. On. Okay. Therefore, in the positive direction, and it is in the negative direction. That's what the condition that I have seen so far. Okay. Now, what about this condition and this condition? What are the top conditions? For example, we'll take one example. Okay. For example, for the first case, this is the case number 1, case number 2, case number 3, case number 4. Okay. For the case number 1, can you please tell me what is happening for the case number 1? VC minus of VS. Okay. So this is the negative direction. For example, minus 1. Okay. Now, what is this VS? It is also in the negative direction. Minus values. Okay. For example, this is minus 1, for example. This is also minus 1, for example. Then what becomes? 0. Okay, fine. This is 0. Let's take another example. This is minus 1. Okay. This is minus 2, for example. It becomes 1. Okay. Minus 1, for example. Minus 5, for example. It becomes 4. Okay. With the VGS, even this has happened to almost all the negative values of the VGS also. But what we can say that if the source potential is decreasing in the negative direction, more than that of the gate, definitely the MOSFET is said to be off. The MOSFET is said to be off condition. Sorry, I'm so sorry. It is on condition. It is on. If the source potential is more negative than the gate potential, the MOSFET is said to be on. Okay. These words you have to remember carefully and then tell me whenever I'm asked. Okay. Okay. Therefore, this is it is also in the negative direction. Therefore, said to be on. Said to be on. What about the last condition? What is the last condition? Both are increasing. That means, for example, this is for example, case number 2. Sorry, 4. Case number 4. Right, VZ minus of VS. Okay. What is the one condition? Give me one condition that VGS is positive value. For example, plus 1 volt I'm giving. Okay. What about the VS? Also positive value. For example, plus 1 volt. Then what will happen? This is 0. Under this condition, because it's less than threshold voltage, then definitely it will be off. But what if it is plus 2 volts I'm giving and plus 3 volts I'm giving? What is this one? Minus 1. So, for example, plus 3 I'm giving. Here is plus 5 I'm giving. What you can observe? Minus 2. What will happen here? It is okay, of course, it is a positive direction. Yes, positive direction. What is happening? It becomes off transistor, right? The transistor becomes off. So in the positive direction, it is increasing. It is also increasing in the positive direction. This becomes off. Okay. So what is the conclusion that, for example, if I take the gate potential and source potential, you are increasing the gate potential in the positive direction, okay, and reduce the potential in the, increase the source potential also in the positive direction, okay. Then what will happen? As long as the source potential is increases in the positive direction than that of the gate potential, then the transistor becomes off transistor. See the comparisons. The comparisons are, we have to compare the gate potential to the source potential in order to make the transistors on or off. Okay. If you want to make the gate potential is less variant than that of the source variant, okay. If the source is more negative compared to that of the gate, then it becomes on. If it is more positive than that of the gate, for example, then transistor is off transistor, right? That's what I have mentioned here. Okay. So therefore, please remember, whenever you see the gate here like this, okay. Okay, VC, VS. Okay, it is said to be on. Please always remember that the gate should be in the positive direction and the source will be in the negative direction. This is the absolute way of understanding about the gate to source potential, whether transistor is on or off. Okay. For all other cases, just you think about it and go ahead, whatever the rate is. Okay. Now, this is enough about this one. Let's go apply the same concept on the PMOS transistor. Okay. We'll take 5 minutes and we'll do. Now, look at this one. For a PMOS transistor, what is the required condition for the PMOS transistor set to be on? So, for example, if this is the threshold voltage of this transistor, if you apply more negative on the gate, then the transistor will be on. If you apply more positive on this one, it becomes, therefore, it is actually on transistor. This is actually off transistor. Look at this particular board. Okay, look at this particular thing here. For example, if I apply some negative potential here, what will happen? You're applying the negative potential and the gate. Negative means negative value. Okay, negative charge. Okay, what we can observe? Pulse will be induced, right? Pulse will be induced. Okay, if you apply more negative, which direction that we are going? More negative means this side or this side? This side or this side? Left side. More negative means that point -2, -3, -4, so on up to so forth, the negative direction. If you apply the more negative, then what will happen? More carriers will be available. That means if you're increasing the negative VZ value in the negative direction, the channel will be formed. Okay. Therefore, what we can say here, look at this one. Shall I write like this? Look at this. VGS value is greater than threshold voltage. I'm so sorry. It is less than the threshold voltage. Can somebody help me? What is the meaning of this one? Of course, in the positive direction, VGS is greater than VTH in the NMOS transistor. It doesn't have any problem because it is all the positive quantity. But about here, VGS is less than VTH means that what? What does it mean? What is the meaning of this one? That means the difference between the gate and source voltage must be a negative value. The difference between gate potential to the source potential should be a negative value. That also must be less than that of the negative threshold voltage. Less than that of the negative. So negative threshold voltage, this is what the negative threshold voltage is. Less than this one, all the values will come into the picture. Okay. Therefore, that's the reason why when VCS value is less than VTH, the transistor becomes on. Okay, let us take some examples and understand how it is. Okay. For example, as I mentioned the previously also, let us consider this is the VG is less than VTH, right? This is a condition. Let me consider the VG and VS. Okay. What is the difference between these two? It should be negative. Very good. It should be negative. But what is the value of this negative value? -1. Okay. For example, we have taken -1 volt. Okay. Right. Now, let us take some example. Let us take something here. When here is, let us consider VC. This is the VS. Okay. For example, 3, 2, 1, 3, 2, 1, 0, -0.5, -1, -2, -3. Okay. Let's here also 3, 2, 1, 0, -0.5, -1, -2, -3. Okay, let me know. Now, what value is the VC, what value is the VS? Make sure that the PMOS transistor is on. In which direction of VS you have to go, in which direction of, sorry, VC we have to go, which direction VS we have to go. VC should be, one possibility is that we have to go to the negative direction. VS should be on the positive direction. Okay. Therefore, for example, look at this particular one, -1, right? For example, this one. Okay. The positive direction. For example, this is the way. Okay. So therefore, for example, -2, for example, minus of 0. Therefore, it becomes -2. Okay. Therefore, minus of 2, minus of 1, for example, it becomes -3. -2, minus of, sorry, +2, that becomes -4. Like this, we have to go. So therefore, what is the required condition on this one? Undoubtedly, let me take this one and copy and paste at this place. Okay. Now tell me, what is the required condition on VCS so that the PMOS transistor becomes on? should be in the negative direction, right? Okay, it should be negative direction. Make sure that that means the negative charge we are putting on top of it. Therefore, automatically channel will be formed. Therefore, transistor will be on. Okay, and also make sure that VS should be in the positive direction. In the positive direction. Okay. If you are in the lab, for example, I have given you the MOSFET, for example, PMOS transistor. I want to say that, okay, just make this transistor is on. Then what you have to do? You have to apply the VC apply the more negative side, VS at the more positive side. Then definitely you will get the transistor becomes on. Okay. What are the other possible conditions? As we have seen, this is the approach. Let us go and understand this one also about this. So one condition already, required condition I have mentioned already, but let us see what are the different other possibilities. Okay. What are the other possibilities? Let me go and remove all these things and let me know what is this one. What is the damn sure condition? VC must be less, negative direction. VS must be in the positive direction. Okay, negative and positive direction, this becomes on. This is the one condition. What about damn sure conditions? It should be off. VC should be positive. VS should be negative direction. Okay. Therefore, this is also off. Now, what about the case 1 and case 4? We'll take one example. Okay. What is the one example? VC minus of VS. Okay. Now let us take, this is actually negative direction, right? -2, let me consider. What about the VS? VS is also negative direction, -2, for example. Okay. Altogether, what this is? 0. Okay. Okay. -3, for example. -6, for example. That what is happening here? +3, right? +3. Okay, -5, -10, for example. Let's take an example. This much voltage we don't apply actually. What is this value? +5. See, look at what is happening here. The difference between the gate and source is actually becomes positive. Therefore, it is off, right? Because as we can see that for all the positive values of this particular one, the MOSFET is actually, you can see all the positive values of VGS. The MOSFET is off. Okay. Therefore, I can say this is a off transistor. Okay. Now, what about this condition? It becomes on, definitely. Okay. So we'll take one example. What is the one example we can give? For example, if I ask what is the one example? In the positive direction is, for example, +2 volts, for example. Okay, minus of. In the positive direction, what we can give? For example, +3, for example. Okay, that this value becomes, what is this? This is also positive direction, right? Okay. Plus, what is happening here? -1. For example, +3, +7, for example. What is happening here? -4. Okay. As we keep on, increasing the source potential more and more in the positive direction, okay, it tends to on. Okay. And the drain potential or the gate potential also should be more positive. Okay. Okay, that's fine. Okay, let me conclude here. And what is the conclusion here? This is what the PMOS transistor, right? Okay. This is what the gate potential. This is what the source potential. This is what the drain potential. Look at this point and we'll do. Okay. Now see, what is the comparison between VZ and VS? If the VS value is more negative, definitely. Okay. So the transistor should be on, more negative. Okay. Therefore, it should be more negative. What about in the same condition? What should be? It should be more positive. Okay. It should be more positive. Am I right? Okay. Therefore, we always try to think about it. The gate potential of the PMOS transistor should be as much low as possible than that of the drain potential. Sorry, source potential. Okay. If I say that the source potential is negative direction I'm going, okay, and PMOS is actually the gate is positive direction I'm going, for example, then definitely the transistor becomes off transistor, right? So these are the possibilities about the source potential and gate potential. Okay, the moment when the circuits come into the picture, and if you ask you to whether the transistor is on or off, and by the potential of a gate and the source, you should be in a position to say that whether the transistor is on or off. Okay, so fundamentally or blindly, that you have to remember that one important thing is that for the NMOS transistor, gate should be higher than that of the source potential. Whereas PMOS transistor, gate should be negative direction, more negative than that of the source potential. More negative than that of the source potential. That's what you have to remember. Okay, we stop here. Now afternoon we'll take another.